So thank you very much. Hello, everyone. Welcome to this webinar. I will talk about AI-driven image analysis today. And as Milena say, Florian Heymans will present at the end the Center for Imaging, and Christian Jacques will speak about the deep learning for industrial vision. This webinar is about image analysis, and we have also very soon a course that we do with the Formation Continue UNILE PFL. So it's a 4-day course on image analysis in the age of AI. We have a slide at the end to advertise these courses. So as a start, I would like to give us a few definitions about what we speak about, because imaging is pretty vast and there is different discipline, I should say. So everything starts with the image acquisition. Maybe you have an image, or you want to capture a photo of, let's say, a very famous Swiss animal, which is the Dahu, and you need to take some instrument, let's say a camera, or could be a microscope or something like that. So it's an imaging device to make the acquisition of the real samples. So that's the first part that we have, the first discipline. So it's the imaging. Then we have other disciplines. And I would say that this discipline I can explain by what is the input, what is the output. So typically the first step is the image processing. So image processing, input is an image coming directly from the camera, the raw data, and the output is an enhanced image. So we do some operation to improve the quality or the contrast, or we denoise or we deconvolve the image. So that's all the operation that we do in terms of image processing. So input image, output also an image. So at the end, we have a nice digital image that we can send to the next operation, which is the image analysis. So that's the most important operation, obviously. And the goal of the image analysis is really to convert these pixels to an object, measure, decision, to something, numbers or something. There is another step that which is very often hidden in the system, which is what we call image reconstruction. In fact, some of the device do not capture directly an image. So they capture, maybe it's a sensor that do some measurements, and we have to convert these measurements to images. That's typically the case for computed tomography, that we record projection or absorption of X-ray typically. So that's a very important step. And there is also other discipline, which is the computer vision, very strong link with image analysis. So in computer vision, input is an image, and the output is a description of the image like a human. So computer vision is very linked to human vision. So we try to describe the image as a human. And there is another discipline that we do not speak today. It's a computer graphics. So that's the opposite of the computer vision. We give a human description of a scene and we convert to an images. So that gives a bit the landscape of imaging. And what we talk about today is image processing, image analysis, and computer vision. So an important aspect of the imaging is what we call integrative imaging. So maybe at some point in your company, your boss asks you to design an image analysis system. So you will go first to acquisition, imaging, then image processing, image analysis, and at the end you need to interpret the result. But there is a strong link. So when you design an image analysis system, is not only the data computation, is also the fact that you have to understand very well how to make the acquisition. So everything is linked, everything is interdependent. So there is few claims that we can say like that. So image dichotomy of the imaging dichotomy. So the fact that the hardware is very specific to the application, but the image processing, image analysis are transversal. It could be independent of the application or the domain. And at the end of the day, what we want to do with image analysis is to make a quantitative analysis of the images. We want to turn image to something useful, measurement or decision or something useful. So we were really to want to quantify the images. So that's all that we have in the image analysis. So what's happened now in imaging? So many things move very, very fast in imaging. In these three domains, so in the acquisition part, we have now intelligent sensing. Typically in microscopy, we have a smart microscopy where we want to drive the microscope to acquire only the data, the relevant data at the right resolution, right spatial temporal resolution or spatial resolution. So imaging sensing. In terms of analysis, obviously we have a lot of impact of all the modern tool provided by the AI, and this very nice model that we have now with deep learning models. And also in terms of visualization. So there is new way to visualize specifically because we have now multidimensional data that can help to reveal some unseen information. So that's for the trends. So we speak a lot about image. But I would like to define a bit more in detail what is an image, because there is different facets of an image, I should say. So what is an image really? So obviously that could be the photo that you take during your vacation. So it's an image, okay. But we are not concerned too much by that aspect. So an image, for most of the people, for experimentalists, I should say, it's a picture. So that represents qualitative information that you want to observe as a human. It's also tools to communicate information. So it's with this motto, seeing is believing, obviously. And for a computer scientist, an image is a set of pixels. So group in array, or now we say tensor when we have multi-dimension. It's to help to archive phenomena or to make some processing or to take again to decision. So at the end, we have only an array of pixels. So that's a way to see an image. But there is other way to see an image also. Sorry. So more the engineer, the mathematician, or the signal processing like me, they see the image as could be as a mathematical function. So also it's a way to design very efficient and optimal operation if you think that an image is finally a mathematical function. Other aspect, the physicist, they see the image as a signal. It's a response that capture the real world properties of something, of some phenomena. So it's also very linked to the measurement. And in the AI world, you can see the image as a piece of data. So like a text or a piece of knowledge, like a text could be represent some knowledge, image can have some knowledge. And all the goal is to make some discovery from this knowledge. From the machine learning people, that's really the image is only one block, one unit of a huge data set that where you want to that you can use to learn something. So there, you see that there is very different facet of the image, and we should never forget that an image is the way that you see an image could be very important in terms of image analysis. Um, so, as I said, for the when we make image analysis, it's independent of the field. So at the end, here I have an image which is probably a pixel represents some nanometers on the top. Here, an image with astronomy, a simple pixel represent millions of kilometers, and but it's the same kind of information that you manipulate. So everything is embedded in images. So image is something that image analysis. It's something that it's across the scales and across the fields. So you have here many examples where images are different scales and fields. And at the end, obviously, what we want to do is to sing something which is probably not invisible and to make quantitative data analysis. Here I have a slide to give a bit, it's a slide about to show that the image are very important, has a lot of impact in every engineering sectors and in science in general. So I pick up some examples. So, and what I want to say through this slide is also the fact that we have different modalities, so different way to acquire the images. And the data source could be also different. There is various way to capture the image. On the left, you have the visible light. So here we collect photons at the end of the day. That's when you take a picture is what you are doing. Even in astronomy, you collect maybe photons. So you just take a light. So it's the visible light. So it's an electronic waves. So there is also the non-visible waves that you can capture if we think about thermal imaging, remote sensing, fluorescence microscopy or so, X-ray. So it's electromagnetic wave. It's not photons, it's something else, but we can make image with this information. And on the other side, you have also the non-electromagnetic imaging. Here we collect something else. So typically in MRI, in medical imaging, ultrasound, it's easy to understand that what we capture is the reflection of an echo of a sound. So it's not photons that we capture. And there is many other examples, typically and also in electron microscopy, obviously in cryo-electron microscopy, atomic force is a displacement. Phase contrast microscopy, here we collect the phase shift of to build at the end an image. So the data source could be very variable. It's not only light that we collect. So now there is another way to also to generalize the images, and typically there is this very important 3D images. So here we have now not only two axes, X and Y, but we have also a Z axis. And we are calling now not this unit not only a pixel, but some people call it a voxels. So obviously the volumetric data is important because the nature is by definition is 3D, and so we want to do 3D measurements. Here I have an example that I pick up in that website. Maybe you see it's a little bit small, but you see on the top here you have a 3D acquisition of some particles moving, and here you have just a 2D acquisition. So it's like a projection. So obviously, if you need to count the number of particles, it's very useful to have the 3D information. If not, you make a lot of error that is full of ambiguities. So by definition, so volumetric data brings something very important in terms of measurements. So by preserving the structure, connection, spatial relationships. And if you want to exploit this 3D information, it's pretty tough, okay, typically for the deep learning model, because you have to take care about the true geometry representation, but it's offer some kind of new opportunity to have a better analysis of the data, because the model can maybe capture all the kind of relationship between object in any kind of direction. So that's improved the quality of the analysis. The 3D, we have another challenge with the 3D is the visualization. Okay, we have all a flat screen, 2D, okay, and we want to see 3D data. So you have to find some kind of tricks. So in medical imaging, they use orthogonal sectioning. In other field, you can make a 3D volume rendering. So here we have a nice micro CT scan of a snail, and you can see the Z direction in the time, so creating a movie, or you can make a maximum intensity projection. So you project and you see here, because the object is pretty white, it's easy to guess the shape of the object. So you have to find some tricks to make the visualization, to make possible the visualization of 3D data. Other challenge that we have in when you want to manipulate 3D images is these, I say, engineering and IT challenge, because okay, it's all the things you have to find a trade-off between complexity, efficiency, and the very important thing is we should be able to try to design through 3D models. And because most of the systems now works by making a 2D analysis, and then we make slice by slice or frame by frames, and we after all, as a post-processing, we collect the information. But if we want to have a very system, very robust, and specifically we're using deep learning, we should find a relation in the same time in all the direction, which is pretty costly in terms of computation. 3D. So now we can move to add another dimension, let's say the time dimension, temporal dimension. So by adding time, you shift image analysis from structure to now to process. So there is new opportunity also to find other things by adding the time. So it's help to quantify, let's say, velocity, motion, deformation, diffusion, and interaction, and so on. And it's really, you have access now to some kind of processes, event detection, growth, or monitor a system, a process. Here I put an illustration of the sky. So you see to also understand that the fact that on the pixel, in fact, we also always consider that pixel contain spatial information. But if you let the exposure time for a very long time, in fact, you can put in the pixel also the temporal information. And obviously, with this time dimension, there is also opportunities to create very good image analysis systems using also AI by learning temporal pattern, predictive some trajectory, also reducing the ambiguities, because when you have several image of the object, you can guess better. Maybe there is some occlusion at some point, so you can guess where the object is. And obviously, you increase also the robustness by having more information. So that's also a new way to see the data. I have here a few illustrations. I don't know which one is the first one. Okay, here it's a droplet that we acquire with a very fast camera, and we obviously with optical flow, it's imaging techniques that we have. We can see the kind of deformation. Next one, which is feature tracking. Here we use a foundation AI model to track the features. You see that we are able to track the aorta in the medical imaging. Here it's object tracking. So here we detect it's a bacteria that we detect in the phase contrast images, and then we detect each of them. We track using also a deep learning model to create at the end the cell lineage. So that's full of example of that we have with this temporal dimension. We can go more. So now we have seen X, Y, so that the 2D images, adding the Z dimension, adding the time dimension. But at the end, we can very often speak about 5D images with X, Y, Z, time, and channels. So spectral information. So I have here a movie also in bio. Here you see that there is two channels that was acquired at the same time. We select the Z information. We go deeper or closer to the objective, and we have the time dimension. Here we see the cell that are dividing, and we can play the time as a movie. So here we have a 5D dimension, and playing with this 5D is very interesting. That we have to think really to multidimensional information when we are planning imaging in a way that we can anticipate AI needs. That's pretty impressive. Okay, in terms of application, there is many kind of application. Should say there is, as we can say, there is mostly two fields. So there is the machine vision, and Christian Jacques will speak about that one, that aspect, to make quality control, visual inspection, defect detection. There is many application also in the food industry, in manufacturing, watch industry, and so on. And there is another one which is that we can call computational imaging, where we have to manipulate this multidimensional imaging, correlative image reconstruction, to collect all the information using a lot of AI also. When you are faced to an image analysis problem, so there is two paradigms, I should say. I don't like so much, but okay, the older time are on the left, modern time is maybe on the right. So you have an image analysis question. So now you can think about using here it's about method. So what kind of method you can use? So rule-based method, model-based method that thinks it's a human that thinks about the problem, an engineer that design a workflow to have a succession of image analysis operation to detect visual feature. We can also model the acquisition system to have better results. So everything is driven by physics. So that's so what we inject as a human is the model, in fact, the modelization of the operation that we have. In the machine learning and deep learning side, what we have to design is a learning workflow. In that case, the effort is on the data. So we have to create a training data set. I will speak about that aspect to finally to train classifier or to train neural networks or to use a pre-trained neural networks. So everything is guided by the data. So it's very two way to see the world. In some aspects, some people try also to mix these things to have something which is hybrid. That will be very interesting also.
Okay.
To things like that. But that's always the question that we have in image analysis. So I would like to speak about the kind of tasks that we have in image analysis. So most of the people have a segmentation task, so image segmentation. So when you take an image, you want to segment this image in different compartments, different segments. So the sky, the sea, the sand, people's ear. So here it's something that we call also pixel classification. Each pixel is allocated to one class, sky, sea, sand, and so on. So it's called segmentic segmentation. Another way to see the segmentation is to say to detect object detector. It's what we call instant segmentation. Each object is an instance of object of interest. Here we are maybe interested more about the people that walk on the beach. And the complete one is called the panoptic segmentation. But segmentation, so it's 90% of the people have a segmentation task. But there is other kind of task that we can do with image analysis. There is a classification. Classification, so you take an image and at the end you want to say, okay, that's a cat, that's a dog, it's in my image. It could be the complete image, or it could be some crop of the image. So there is maybe some pre-processing operation that crop on the area of interest, and then we classify the crop. The style transfer is something that we can do only with AI, and that's very interesting also. You have to, probably this famous painting of La Joconde, which is mixed with the style of Van Gogh here. So that's for the art, it's very interesting. But in industry, you can use also this kind of style transfer to make in silico acquisition. So you acquire with a modality and you learn another modality. And after you avoid to acquire the image in the two modality, you use only one modality and transfer the style of the modality to the other modality. Restoration, obviously, you can, that's mostly an image processing operation. You can improve the quality of the image by making denoising, deconvolution. Also, that's very useful, obviously, to detect the object. In painting, it's another way to that we also really related to AI because we use a lot of data to make in painting is to correct artifacts or maybe to make super resolution to increase the resolution of the image. So that's the task that we have. So important things. So we should define always the task. That's the first thing that we should answer. And after when we have the objective to use the AI, so we should select the deep learning model. So here I have a recap of where we are. I prefer to speak about deep learning than AI because AI it's pretty confusing. We are so that's that's more larger one. So what we really do at the end of the day is something that's more deep learning. And all the deep learning, as you know, start in around the 2010, 12 or something like that. And there is two things that happens in the same time, a huge amount of data that make possible to do the deep learning and GPU, because it's a task that can really parallelize a lot and GPU help to handle this massive amount of data. So that's a way to generate this kind of deep learning model. So I would like to, I speak also a lot about AI models. So what is the model at the end of the day? So that's an architecture and um, a large amount of parameters. So in our field, we have mainly two kind of architecture. There is more, but to simplify the view, we have two kind of architecture. The one which is called CNN, the convolutional neural networks. So it's built with, I say, a large combination of image processing tools that we have all the time. So it's to detect local feature, to organize a spatial hierarchy. It's also very fast and it's pretty mature techniques. And the other architecture is called Vision Transformer. So it's a transformer techniques like the ChatGPT, the T for ChatGPT, a transformer. So here it's more addressing the image as a global view. So taking account all the context, all the relationship between the object or the patch on the object. So it's trained on massive data. So we need a lot of very, very large data set. The advantage of that one that it's ready for multimodal. So the image is decomposed in patches. Patches is a token, is a piece of information, but we can have a token that come from other modality, or even it could be a text or something else. So that's pretty interesting. So in terms of parameter, so as I said, there is if we use a typical model that we have, it's a YOLO or let's say SAM or something, but to the unit, it's very classical model that we have in our field. So they have like 10 million or 100 million of parameter. So it's huge. A ChatGPT is there so to just have the scale. So 10 at the power 11 or more parameter. If we think in the all the time, sometimes we are able also to solve some kind of image analysis problem with very few parameters. In fact, and maybe we have just to tune some threshold or filter, very simple filter, and with 10 parameter, maybe we are able also to solve a certain range of tasks, I should say. Okay, let's move on. So in deep learning, so what we have to say that we have also, I want to fix few words. So the word of training versus inference or learning versus inference. So the learning steps, so everything starts by a learning step. So for the learning steps, what you have to provide is the images, but you have to provide also the labeled image, ground truth images. And that's the difficult task to have these ground truth images. What is true? what you want to do. Typically, if you want to segment this kind of cells in the images, you have to outline all the cell one by one in many, many images. Then you can train a model, and at the end of the day, you have your model, you save your model in the zip file, you are happy with that, so you have a trained model. Then you can take your trained models and take one image and make an inference, and in the end you have the output. So you are sorry. So you have the output. So the learning is a step which is very costly because you have to design in terms of data. You have to acquire the data. It's the data, then make the labeled images and everything. So it takes also, it's a lot of effort in terms of data, but also in terms of computation. You need very powerful GPU that takes hours to obtain something. It's also risky. I should mention that there is a, you all know that there is the risk of underfitting, overfitting, and so on. So there is a lot of risk, in fact. That's a very painful operation, but you do one time. When it's done, you can make the inference, and the inference, it's very light operation that runs in a few seconds, or maybe now in real time. So in some operations, it could be milliseconds. It's run on a CPU, and you can have a nice prediction. There is another way to see the training is also what we call the transfer learning. So in fact, in that case, you try to find a pre-trained model, something that already exists in your field, in your domain. And you just add few pairs of images. And what you have to do is just to tune a bit the model such a way that you obtain a specialized trained model for your application. So in that case, you probably need GPU for that most of the case. But it takes maybe minutes, okay, let's say, or few hours. It's not so huge depending of the task. Sometimes it could be very fast. So the transfer learning is something which is also offer a sort of new possibility to see to to reduce the risk of to enter into this full training, which is pretty risky and pretty heavy. But all the question here is to obtain or to find somewhere a pre-trained model which is close to your application. Okay, here I did a table which is pretty heavy. Okay, I will try to comment. So the model selection. So where you have to, where you can find, how you can select a model. So I divide the things in 3 columns. So the column is there is some overlap. It's not completely well aligned like you can think when you see these tables. So there is what I call the in-house model, adapted model, and the foundation model. So in terms of in-house model, the idea here is to have something which is very specific for yourself. That the specific, that means it's very narrow in terms of generalization, but you can obtain a very compact model, a small model. So that's the idea here. And if you use more, let's say, an adapted model here, that means you will start by initial. So you have an effort to do in terms of training. So adaptive model, so that means you will start with a domain-aware pre-trained model. So it's a model which already exists, and you will just fine-tune this model using GPU. But in that case, the number of images that you have to put it is pretty small. So that's a limited effort that you have to do to adapt your model to your domain. So in that case, you obtain something which is pretty interesting. And compared to that one where you have to do a full training on GPU, the initial model is random. You start by, you do not have a model, so you have nothing. And in terms of label image that you have to provide, typically for an image segmentation is maybe 100 or 1000. So it's huge compared to that one where it's may sometimes limited. Sometimes you can just, in that case, with 10 images, 20 images, you have already some kind of results. So that's to compare a bit the in-house and adapted model. So in terms of interpretability, obviously in the in-house model, you can control everything because you control the data. You can very easily maintain. Maybe if you want to improve your model, you can just add images. You have a completely, you are trustful in your system because you know the data that you have to put in the systems, and the inference is very small, is very short in the run on the CPU. In the foundation model, in that case, you do not make any training. So it's what we call zero shot. And so you take the model as it is, usually. So some people try a bit to make to train, but in principle, you use the model as it is. So uh, so it was trained obviously on, but not by you. It was trained by the provider, the vendor of the foundation model. It was trained on massive data, and here there is a high risk of you have a strong dependency to the data. But for foundation model, which is interesting, that the fact that it's a generic, so you can apply this model and to many kind of data, even the data was not in the training data set. So it's what we call the generalizability of, which is pretty universal. But usually this kind of model are very huge. So there could be some of the model are this, have the size of 1 GB. In terms of trust, so here it's pretty opaque. You don't know exactly what you are doing, okay? And sometimes because it's a so huge model, when you make even to make an inference, it could be very slow running on the CPU. I put few names of very famous model that we have in our field. Sorry, here. The UNet, so it's more an architecture that I like it very much. So UNet typically it's an architecture that you will use if you want to make an in-house model. So that's the typical architecture that you will pick up in first to try. And that one. The other one, like CellPose, so CellPose, let's say YOLO, it's probably a pre-trained model that you will have to fine-tune to obtain. So fine-tuning, so to adapt to your exact data. But typically a YOLO, this kind of object detector, it's pretty easy to fine-tune to your problem. So if you want to detect object in images, maybe that's one of the first options that you can choose is this YOLO, and you will add few bounding box around the object of your interest. And with a step of fine-tuning, you will be able probably to detect your object. Other example of foundation model is maybe SAM, which is a segment anything model of Meta, which is a very heavy model, but they claim that they can segment anything in the images. Like the Dino, they claim that they can extract any kind of feature in any kind of images, not only images of fraud, but it could be images, medical images, material science images, anything. That's their claim. Okay. So the question is how we trust this kind of models. Learning strategy. Yeah, will be fast here. Learning strategy. So we have mainly two way to see the learning. So by decomposing each steps. So let's say pre-processing, denoising, segmentation, classification, decision. So each step we can use a AI model to do the task and so on. And okay, that's the advantage of that one is that we have a better explainability because we have a point where we can have a look on the images. So we are trust this kind of system, and it's less data hungry. The opposite way, and people moving a lot in that in that aspect, it's end-to-end learning where you have a global optimization. You have the input images, and at the end you have a decision. Here, in that case, for an organoid is valid or non-valid. That's it. And so that's true, false. Obviously that's limit the error propagation. When you have several steps, that there is a risk of error propagation, but it's less reusable. I should say that that one it's a pretty smart strategy because maybe you can think that one of the model could be a pre-trained model, so you don't need to train because if you are confident that the denoising works well, a pre-trained model for denoising works well, you will use it directly without any. So that reduces the quantity of data that you need to use. But you can also handcraft some of the model. Usually, what the one that we we design for us is the last steps, or you can design your custom model. So maybe you will design the classifier also in terms of machine learning using random forest, or maybe a non-AI solution. So when we are looking at an image, I like to see the image with different compartments. So obviously you have the pixel, as we say, but there is other kind of things. There is the visual feature that you have. You have maybe have some patterns, texture. You have a geometric organization. You can link object by graph and so on. But an image, I like to say that you have to really have an expert eye on images, and certainly for training a deep learning model, that's what you need to do. So what is the quality of the image in terms of noise, acquisition artifact, resolution, calibration, stability if there is movement during the acquisition and so on. So how reproducible is this image? So the quality is something that you should assess before any kind of training. You can see the image also in other domains. So I put it the classical domain that we have in in the older time. So we can see the image as a frequency using the Fourier transform, scale pace, or wavelets. So we change the domain, so the way that we represent the image. Another modern way to see the image is to embed using a model and to learn something in the latent space. So we reduce the information, we encode using AI model the image in a latent space, and we observe what happens in the latent space. That's also a new way to see, to approach an image. And an image also, you should consider the data representativity of the image. Is this image is really, because very often you have many images of the same sample, same system. But is it just a unique case, a rare situation, or is it something that happens very often? And that's something that you have to see. And a classical way also to transfer the information of an image is to think about the semantic of the imitation, what kind of description you have, maybe using LLM. So a few claims here. I have to be fast. So AI image analysis is limited by data, not by algorithm. So the data is the code itself. So you have really to develop your training data set by making curation, labeling, validation, and bias. Machine learning is as good as the image data that you put inside. So there is several ways to find ground truth data. On its strategy, I will skip that one to finish by that one. If you want to shift to deep learnings, so the first thing that you have to do is the first question, do I really need deep learning? Maybe other solution, more robust, more stable, could help me. If yes, if not, you can try to find a pre-trained model that already exists that you can fine-tune here. And the question of the learning. And to finish, so there is also practical consideration, very important. The data resources that you need to train a model. And there is few things that you won with the deep learning, but also other things that you lost. What you learn is the generability, the adaptability to the data, multimodal, using transformer, fast answering, end-to-end task validation, possible discovery. And you lost many things also. The explainability, error analysis, stability, image skills, because imaging skill, image analysis skill, we lost because it's so easy to use that people don't know how to do image analysis. So that's the end of the presentation. I have one slide now. Lena, can I present the slide of the now?
Sure, sure.
Yes.
Yeah, go
Yeah.
ahead. Yeah.
You see that all this image analysis is a pretty could be seen as a pretty difficult task. So having skill to be able to design efficient imaging workflow in the age of AI, it's very important. So it's why we have decided to organize these courses. It's a 4-day courses that will happen in March and April. It's a mixture of technical core and more perspectives. So, and what it's important to notice, it's independent of the application agnostics. So the learning objective is to gain insight in cutting-edge imaging techniques, develop the expertise, but also to practice, to have hands-on skill in software and AI to design very efficient image analysis, explore the opportunity and the risk of AI. It's a bit what I have done, and to learn the best practice in image analysis, how you can start to design an image analysis with AI. Yes. Now I will give the floor to Florian. Florian
Yeah.
Emmans is one of the member of the Center for Imaging. Okay.
Hello, everyone.
Hello, Florian.
Thank you, Danielle. So I'm one of the members of the technical team of the Center for Imaging, and Danielle is one of our collaborators as well. And I'm going to tell you a bit about what the Center for Imaging is and how we can potentially help you. So our mission is basically threefold. We want to provide the resources that are necessary for image analysis and image acquisition at EPFL. And the way we do that is mostly through software that is interesting for the community that we develop in-house, or we take software developed by labs and make it more accessible and promote it online. We make it more accessible as in we're applying best practices and to make it more robust. Then we support academic and industry partners with through consulting on specific projects and in some cases implementations of image analysis pipelines. And lastly, we do trainings like the course that Danielle just mentioned. Okay, so what are the kind of tasks we can help you with? We can analyze existing images for you. In many cases, those are for metrological applications on relatively few images. So we work with R&D departments or labs at EPFL to do that. But we've also had cases where people have many images and they want to process them in real time. And we've developed the automated image analysis pipelines for those collaborators. We've trained custom neural networks for specific applications, and we can also help you upstream by selecting the right modality or consulting on which modality you should use for a specific question, which imaging modality, what technique, and then when it comes to the acquisition, how you should choose the camera and what settings you should choose for the camera. And if you have a very specific research question, we can also link you to match you with a lab. So we can create connections between industry and labs at EPFL. Yeah, that's already it. If you're interested or if you have a project that you think we might be able to help with, please reach out to us and you can write to imaging@epfl.ch. And down here you can see the team. Okay.
Thank you. I shared the link of the center as well in the chat. So yeah.
Okay. Thank you.
Thank you.
So now we can... Christian Jacques, are you
Yeah,
there?
vous m'entendez? Ça marche?
Oui, oui.
Okay, I might have to speed on a bit because I'm at the customers and I may have to give up the room. So let me just quickly share my
You're a
screen.
bit late.
Yeah, no, it's fine, it's okay. So, okay, here. All right, can you all see the screen?
Yes.
Okay. So thanks, Daniel, for a very interesting talk. And I think you said basically everything I will say. So today I'm going to talk about some challenges when using deep learning for industrial vision. So maybe just not everybody is familiar with industrial vision. You mentioned that Daniel, machine vision as one of the field of applications for imaging. And in my case, so it's really specific. It's a really niche part of all the imaging field. But in our case, what we do is install industrial vision applications on industry, like on automation lines. So typical applications would be medical needle inspection or weld quality check, some semiconductors quality check, MEMS analysis, characters reading, and lenses inspection. So as you mentioned before, Daniel, it's mostly either segmentation tasks or objects finding tasks, typically finding defects. And again, this is quite specific to industrial vision. It's not as broad as imaging, but the way a typical project is undergone is you get a request. It could be from a customer or within your own company. You run some tests in a lab to find the best image, the best solution you can offer. You get a quotation, so you propose a solution. Once it's accepted, and that's a pretty iterative process, it can take a lot of iterations here. Then once the quotation is accepted, you move on to actually doing the project. So you buy the hardware, you implement everything in-house. Then you move everything in your customer's site. You have a super important validation step, and eventually you get customer support, and that can last for a lot of time. And one thing that is quite important to understand in our field is that once you get a quote accepted, you have to deliver. So it's I'm a bit dramatic here, but it's kind of game over. Once the quotation has been accepted, you have to do what you promised to do. And maybe you can see here something where deep learning can be hard to use. And I will just illustrate why this is problematic in the case of vision, because vision is super sensitive to change. And it happens a lot that you will have a customer changing something on its process, on its line, on its components. You'll think it has no impact. And actually, the image you get is very different. So this is an actual project I was working on a few years back. And we just got like 4 or 5 samples of these chips, and we had to read the text that's printed here. And actually on the line, the text can be really ugly. The contrast can be really bad. The chips may be dirty. And it's pretty hard to explain to a customer why it reads fine on some chips and not on others. I had the case also where someone called me telling me, hey, the vision system is doing garbage. There's nothing working anymore. And when we connected on the line, so on the left, you see what the image was supposed to look like. And when we connected on the line, this is the image we had, because they did some maintenance and they moved one of the illumination, one of the lights they moved. And this had a huge impact on the image we got. So of course, the vision system, the vision algorithm was just rejecting everything because it was expecting to see something like on the left, and it had something like on the right. Or my last example is we had to check for these 2 bright spots are metal on metal welding, and we had to inspect for the quality of the welding. And the customer had to change some parameters of the welding process. And this is the end image we got. And they just did a few adjustments. And I think I get my point across. I'm meaning to say vision is super sensitive to change. And in this regard, it's easier to have an algorithm where you just have a few parameters you have to tweak, rather than a big deep learning model that you have to retrain every time something changed. So to put it in perspective compared to the standard vision project workflow, here's how you would integrate deep learning in a vision project. So you acquire data, you label it, so that takes in the order of days. You build and train a model that you try to validate, and you get usually not at the first try, but you see whether your model is satisfactory. Usually you go back to acquiring more data, and eventually you get something that you can think of deploy. So my point here is you never know how many loops, how many iterations you will need to get to the required performances. And this can be really problematic when you sell a project, when you have to tell a customer, okay, if I need to find all the defects on your watch glass or whatever, here's the amount of time I will need to be there. You don't know that beforehand. So the message for me here today is just to say, as you said, Daniel, do you really need deep learning? Basically, if you can avoid it, well, you should. And I've shown some examples, but vision or imaging is really everywhere. And it's really sensitive to a lot of parameters that sometimes you do not control. Deep learning is super powerful, but as Daniel explained, it's super costly to build. And what do you do? How do you adjust when your data changes? So like, I'm calling it data drift, but there's many different names for that. How do you basically maintain a deep learning model in production over a long period of time? And I will close it on a bit of a cliffhanger, but I will give some answers to that during EPFL imaging class in March and April.
Thank you, Christian.
Sure, thanks.
Thank you. I have seen one or two questions on the chat. Can I answer to that one, Milena?